Well, what we are going to do now is to see the geometry of the tangencies. Before we have done the tangency between the different solids of revolution we have on the screen, taking advantage of a common tangent plane sharing a common tangent point. And now we are going to work with the 3D geometry we have done in a 3D sketch when we were defining our solids of revolution. So I'm going to start making visible the 3D sketch of the sphere. We can see that we have created a tangent plane when we did that. I'm going to make also visible the 3D sketch of the cylinder, where we can see the geometry we use, the axis of revolution, the generatrix, the circle of the inscribed sphere inside this cylinder, and a radius of this sphere, a point on the surface, and a tangent plane to the cylinder passing through this point. So now if we want to make these two solids tangent, we just need to select the two tangent planes we had described initially in their corresponding geometries, and we select the mate bottom and we ask for the coincidence of those tangent planes. This relation is not going to be enough. Remember that they also need to share a point on the surface of both solids. If not, they are not going to be in contact, so they will then be tangent. So I'm going to select the point on the surface of the cylinder contained on the tangent plane, and in the same way I'm going to select also the point on the surface of the sphere that was contained on its tangent plane. Remember that these points were the endpoints of the radius of the inscribed sphere inside both solids. Now I made coincident these 2 points, so now we have finished. The relation is correct, and both solids share a tangent plane and a common point on it. So there are another elements on the 3D geometry of each solid that are important. So I'm gonna create now a 3D sketch and make visible or convert these elements so we can see them clearer, and we understand the relation between the different ones when we have two solids tangent. So I'm going to convert the circle of the inscribed sphere inside the cylinder, also the radius we use initially to create the tangent plane. Remember that this radius was perpendicular to the tangent plane. Converting the generatrix of the cylinder and the axis of revolution. And in the case of the sphere, the significant element is simply the radius also we use to create its tangent plane. If I select now, for example, the plane containing the circle of the inscribed sphere inside the cylinder, we can see, it is in blue now selected, this plane contains both radius of both spheres, both the sphere and the circle of the inscribed sphere in the cylinder, as well as the axis of revolution and the generatrix of the cylinder we had selected. If now we rotate the view and we observe the relation between the radius in black and the tangent planes, we can see that these tangent planes are perpendicular to both radius. Well, so these are more or less the relations important in this case. I'm gonna go back and we are gonna see now, for example, the relations. I'm gonna hide the sketch, the 3D sketch of the sphere. I'm gonna make visible the 3D sketch of the cone, so we can analyze the relations between the cone and the cylinder when we impose the tangency between the solids. We are gonna do it in the same way we have done before. In the cone we had this tangent plane, so we select the tangent planes of the two solids and we make them coincident. Now the tangency is from the inside, so we just ask the software to do the tangency on the other way around. So yeah, we have it. We have now the tangent planes in the middle between the two solids. Second step, as before, we need to make the 2 points on the surface of the solid planes coincident. Done so, we have the tangency between these two solids. So in the same way we did before, I'm gonna make them visible or convert the significant entities to in black to in a different or a new 3D sketch. So I'm gonna select the axis of the cylinder, the radius, the circle of the inscribed sphere inside the cylinder, and also the equivalent entities in the cone. The radius, the circle of the inscribed sphere in the case of the cone, and the generatrix of the cone. Okay, I've selected before the generatrix of the cone, so what was left now was the generatrix of the cylinder. I'm going to also convert the axis of revolution of the cone. So these are all the significant elements in the case of the tangency between these two solids, the cone and the cylinder. Now the spheres, the inscribed spheres in both solids do not fulfill any specific relation, but what we can see is that both radius of both circles are in fact coincident or collinear, okay? This is something that is gonna happen always. We can also observe that both generatrix, the generatrix of the cone and the generatrix of the cylinder, intersect at the point that is the common point between the two solids, the point of tangency. And also we can observe that the tangent plane, if we check it from the side view, both radius of both circles are going to be perpendicular to this tangent plane or planes. This is something that is obvious because we define these tangent planes imposing them to be perpendicular to this radius before, if you remember. Another relation important is that both the bases of the cone and the bases of the cylinder are going to be to the tangent planes. Remember that another condition we could set to set a cone tangent, for example, to a plane was to impose that the vertex of the cone was contained on that plane and that plane was tangent to its base, okay? Well, so something that could be left, if we check the planes that contain the circles of the inscribed spheres, we can see that they do not fulfill any particular relation, but what they do is that each one of the planes contain both the radius of the two circles, okay? We can see that this one, that is the plane containing the circle and the radius of the inscribed sphere in the cone, also contains the radius of the circle of the cylinder. In the same way, if we try to look now for the other plane, we will see that the plane containing the circle of the inscribed sphere in the circle of the inscribed sphere in the cylinder, I'm trying to look for it now, we can see that in fact this plane contains the radius of the circle in the cone. Well, so these will be the relations between these two solids, and now we are gonna see the relations between the torus and the cylinder. The cylinder and the torus, remember that is maybe the more complex solid of revolution, so we'll see that it's gonna be slightly different, but not that much. Well, so I'm gonna make visible the 3D sketch of the torus. Yeah, now we can see its geometry. So now we are gonna look for the tangent plane of the torus. We remember we did two tangent planes when we built this solid. I'm gonna select the tangent plane from the outer part of the torus because it's gonna be easier to place them the tangency with the tangent plane of the cylinder. So I'm gonna select the tangent planes of the corresponding solids and make them coincident. And as before, setting only this relation is not enough. We can move the solids and they are not in contact. So I'm going to select the points on the surface of each solid that are contained on these tangent planes. And now, when these points are coincident, we have finished with the operation. So we have the tangency of both solids. As we did before again, we are going to create a 3D sketch and we are going to convert the relevant elements to this sketch. So I'm going to convert the axis of revolution of the cylinder, the use the circle of both inscribed spheres in the cylinder inside the torus, and of the torus is going to be important from the torus to select also the circular axis, the axis of revolution, and the radius of the circle of the inscribed sphere we used to generate the tangent plane we had selected. So I'm converting all these entities I mentioned, and now we have everything we needed. Okay, so now it's left, the generatrix of the cylinder is left. I'm gonna select it. Yes, so now we have all the elements I was mentioning. If we observe, as in the other cases, the tangent plane is going to be, of course, perpendicular to both radius of the circles of the inscribed spheres inside each solid, and also these two radius are coincident or collinear. In this particular case, we can also see that the generatrix we have selected of the cylinder contacts with the radius of its inscribed sphere. And if we now try to align the plane containing each circle of each inscribed sphere, in the case of the cylinder, this plane is not very relevant. However, it will intersect at some point the axis of revolution of the solid of the torus, and will contain the radius of the circle of the inscribed sphere of the torus. But it's more relevant if we select this second plane containing the circle of the inscribed sphere of the torus. We can clearly see that this plane again contains radius of the inscribed sphere inside the cylinder, okay? And this plane also contains the axis of revolution of the torus. So these are more or less the relations in this case. And as I said before, this will be the most complex solid among the 4 solids of revolution we have on the screen. So, well, this is more or less everything. Just remember that it's important to understand this, because this is going to help us in many cases when we need to do particular calculations or some operations, and not always the software can do a straightforward tangency, or we will need to take advantage of these tangent planes or these relations we have just described to set the tangencies between different solids of revolution.